let's leave the floor to Bruno Paduano from More Energy Lab. He's going to present a work on the influence of the mooring system in dynamics and control.
Okay. Thank you, Mauro, for the introduction, and to the organizer for being here. During my PhD, I discovered two main things. I did my PhD on moored wave energy converter, and I discovered two main things. The first one is that no one likes mooring systems. And the second one is that no one cares of mooring system. Generally, mooring systems are taken in consideration for extreme condition and for the survivability of the device. Of course, it is the main purpose of mooring system. This is the most important one. But we know that in order to reduce the LCOE, in order to reach more important performances of our device, we had to expand this way of thinking to, as also Damian say, a co-optimization control, co-design. So the question arises: if the mooring system influence the device dynamics in operative condition, we are missing something. What I want to say is that we are going in general to apply for our purposes model-based approach, control design with a model-based approach. But if the model is not representative, we know that we are building up a control action that is not representative. From the literature, we know that in general, mooring system can have a significant influence on pitching and rolling wave energy converter. What I did is to test experimentally and numerically the influence of the mooring system on the productivity of a pitching wave energy converter, that is ISWEC, that works with a 2 gyroscope inside. And the effect is that the mooring system can affect up to 20% the productivity of the device. After that, the test has been done with PEWEC, another wave energy converter, but it takes advantage of the pendulum motion inside the device instead of the gyroscopes. And in this case, we were able, by extrapolating the frequency response of the device model of the PTO that at the PTO axis, by extrapolating that frequency response, we are able to perform and to synthesize a more representative control action. But what happens if we are going to analyze EVIM buoy? We know that an EVIM buoy in general is not so much affected by the mooring system, thanks to the because also we know that the heave motion, hydrodynamically speaking, is uncoupled with the other motion in most applications, of course. But if the mooring are influent in the device dynamic, we have to compute a model that with which we are able to perform a representative control synthesis. So the objective of these studies are pushing towards a control modeling approach in order to try to evaluate representative control action, and moreover, just moving towards a control co-design. This presentation is based on the work that has been presented to the IFAC World Congress in July. We know that mooring system the models on which mooring systems are represented are generally highly expensive, nonlinear, and they are numerical models. So it means that are quite complex to be integrated into a definition of a representative control action. The outline of this presentation will be this one. The first part we will see how can we move towards a control-oriented modeling of the mooring system. We will define a benchmark high fidelity model. Then we will identify a representative and computationally efficient database model for the mooring. And after that, we are going to physically parameterize this response. After that, we are going to propose a control co-design approach in order to optimize the mooring configuration, including the control action. The case study in a nutshell is just a spheric tipping point absorber with a taut spread mooring made with 3 different lines, and the PTO is virtually linked just to the ear motion. Of course, it is a simplistic way to analyze a problem, but it is just a preliminary work. The environmental conditions that has been included within this work are from a region from Pantelleria, that is an island in the Sicily Channel. It has one of the most, let me say, advantageous environmental condition in terms of wave energetically speaking for the Mediterranean Sea, and the wave directionality is included in the problem. Just move fastly on the mathematical models. The hydrodynamic is linear based on the potential flow theory. The PTO is an ideal PTO, and the controller is a reactive one with the PI structure. And the mooring benchmark model is a dynamic lumped mass model in order to include all the relevant force into the device dynamics. Okay, how can we evaluate the influence of a mooring system by achieving a model that can be easily included into the definition of a representative control action? In this case, what I did is to evaluate the empirical transfer function estimate of a single line, just of one line, by moving the device at following a signal that is a multi-sign signal in order to achieve the frequency response between the movement of the device and the force applied to the device. Once I did this, it is quite straightforward to apply rototranslational matrix and to refer for each GM tilde that I evaluated here. I guess the pointer is not working. Each GM matrix that I evaluated here, by applying the rototranslational matrix, it is possible to parameterize the mooring action as a function of the line orientation. Now we have to say if the model is able to represent the device dynamic. Of course, it is a simplified model. We know that mooring system response is non-linear, but it could be defined with a linear model under certain conditions. What we did is to compute the database model with the target one, that is the OrcaFlex dynamic lumped mass model. The frequency response to the device has been computed, and the comparison is very good, and the models agree. But moreover, we move from a system that is non-linear to a system that is totally linear. This means that we are able to synthesize, we are able to define our problem linearly, and we are able to move from a time domain representation of the phenomena to a frequency domain representation of the phenomena. What about the control design? The control design has been, the controller has been synthesized by taking advantage of the impedance matching principle. It is quite straightforward to synthesize the control action. At least representative, of course, is not the optimal control action, especially in a regular state, but it is really a straightforward and interesting way to synthesize a control action that is able to tell you something about the representativeness of the model. The impedance matching is able to, in monochromatic condition, to synchronize the excitation force, that is F and Q, with the output, that is the PTO velocity, essentially. The optimization problem aims to the maximization of the device productivity on the wall scatter, which is subject to, for example, the wave data. Each spectrum has been included by defining also the directionality of the spectrum, and the controller is synthesized for each spectrum and for each individual. Each individual I refer to each mooring condition. So we are going to change the angle of the line's orientation, and for each individual we're going to perform a control synthesis that is representative for that individual. And of course, we added some inequality constraints. This is due by the fact that without the inequality constraints, our optimization is pushing the orientation of the line to any line is going to be at the same angle. So to avoid this, we are going to include some inequality constraints to the angle in order to avoid unphysical layouts. What we did, we started from an initial condition that is a symmetrical condition. On the first step of the radius, you are able to see the orientation of the first line. On the second step, you are able to see the orientation of the second, and on the third one, the orientation of the third line. Starting from the initial condition that gives us information of a symmetrical mooring pattern, what we did, the optimization algorithm moves the optimal configuration to an unsymmetrical pattern. In this case, the first line will be almost 60 degrees, the second 180, and the third one close to 300. At this point, we define various models. The first one is a fully unmoored model. This is just to evaluate the influence of the mooring system on the device productivity and on the device dynamics. The second one is a fixed mooring model with the initial condition, just to check if you are going to do control synthesis by leveraging the mooring influence in the control synthesis, by considering the mooring influence in the control synthesis, but without optimizing the mooring configuration, what happens? Then we have the optimized model, and the last one is the model that is achieved at the initial condition, but neglecting the mooring system into the control synthesis. The results show us that the mooring affects the overall device dynamic, and the influence is significant. Comparing the condition 1 to the condition 4, the omitting of the mooring effect will cause a productivity drop up to 40.8%. Moreover, the optimization algorithm is able to increase from 2 to 3, so from the initial condition to the optimal condition of 5.6%. And this is quite interesting because, of course, it is a really simplified case study, but it gives you the possibility of analyzing the problem, the relevance of the problem that Demiano raised yesterday. So we have to move towards a control co-design approach in order to include all the information in an holistic optimization approach. Thank you for listening.
Thank you too, Bruno. Someone from the audience? Yeah, nobody really likes mooring. Yeah.
Thanks, Bruno. So if I understand correctly, your optimization is just with respect to the angles of the mooring lines. Do you think that if you change the mooring dynamics, so for example, clump masses or floaters on the mooring lines, that might change the orientation, or do you think the orientation of the mooring lines is insensitive to the mooring dynamics themselves?
This is a really interesting question. I think in general, at least with the problem is not symmetrical, considering all the wave orientation, all the wave direction, and at least in general, I expect that the results of the orientation of the line will be the same, because it is forced by the surge motion, including the mooring dynamics into the system dynamics. We are going to do something that the hydrodynamic doesn't do. What that means is that we are going to couple surge with diff, and so since these motion are coupled, what happens is that I expect that every configuration, every optimization algorithm changing the mooring configuration will give the same results in terms of angle. Of course, the productivity results will be totally different, but the angle, I guess, will be the same.
Thanks.
Someone first over there. Where? And we have time also for the.
Hi, thank you for your presentation. You are using an optimizer with with a lot of constraints, right?
Yeah.
And it converges. Yeah. That is the optimal solution.
What is?
It converges to, subject to all those restrictions, it does converge. Have you tried or have you considered using something like genetic algorithms to, because here, as Professor Ringu said, you are defining or searching for the optimal angles of the mooring system. Have you considered using something like genetic algorithms to do something like that?
Definitely, to avoid local minimum. In this work, we used both a multi-star gradient-based algorithm and the genetic algorithm. We did evaluate in the last detail the optimality of the solution, but just because this is a preliminary work. But in any case, we use a global optimization approach. And both solution with multi-stars and the genetic algorithm converge to the same results. And so, yes, we analyze the problem analyzing with a global optimization approach.
Okay, thank you.
Thank you. Very interesting presentation. And my question is related exactly to this slide. Have you considered, or can you consider in the future, for example, instead of only maximizing productivity, also considering other variables? Because for moorings, one of the most important considerations of their cost is survivability. So considering some extreme sea states, do you think that this can be included, for example, or how would you do it to consider maybe both of these aspects and optimize it in some Pareto front or something like that?
I don't want to do a lot of spoiler on my next works, but definitely we are going to include the survivability condition of the mooring with some parameters. One could be, for example, the safety factor achieved with and with each individual. And it will be a multi-optimization approach, so we are going to build up a Pareto frontier, as you said. And there are the problem with including of the survivability condition is that it's not trivial to include such a massive quantity of simulation into an optimization, because if you are going to do everything well, following I don't know, the NVOS 301 or other standards, it requires like a significant amount of simulation, and probably we are pushing our linear model beyond the range of validity of the linear model. So it is possible that we are going. I'm just considering to use something that is more interesting, let me say, from another perspective. Like, for example, it could be a focus wave, but taking the dynamic model into the simulation approach.
Thank you.
You're welcome.
Okay, thank you, Bruno.